Okay, this is the 13.4 video. It's on the chain rule. This is kind of a continuation of last section, which was partial derivatives. So this is partial derivatives, functions of multiple variables, but now these are going to be ones that require chain rule. So there's two main types, and then within those two main types, there's we have two variables and we have three variables. So it's going to look like kind of four different formulas, but it's really only two main types, and it just varies depending on how many variables you have, how the formulas look. So we're on page 714, and it talks about here what I was just saying. There's several forms, depends on how many variables are involved, blah, blah, blah. So they have the first one. This is Theorem 5 in your book. I think this bottom one is a lot easier to follow. So here you have y equals a function of, or sorry, w equals a function of x and y. And then x is a function of a single variable, and y is a function of a single variable. So these are like parametric equations where t is the parameter. And so notice that w then, if you plugged in this function for x and this function for y, notice that w is a function of t. So since w is a function of just t, if you were to plug everything in, then when you take the derivative, notice it's straight d's. Straight d's would be for functions of a single variable, which w is a function of, again, just t. All right, and then here, when I write the formula, I'll show it to you in my notes. Oh, wait, here it is. Let's look at this one. This is on the top of page 715. This one makes a little more sense. So w, notice that w, where was it? Here. W is a function of two variables, x and y, and then x and y, if you plug in for them, are just t's, and so it gets it down to a t. But in this form, you have x and y. And so if you did the partial derivative of w with respect to x, this would be curly d's, because it's x and y, so you have two choices, so it'd be partial derivatives. And then the derivative of x with respect to t, straight d's, because x is a function of just one variable, t. And then the derivative of w with respect to y, again, curly d's, because w is x and y. And then straight d's for the dy dt, because y is a function of just t. So this is the formula that I'm going to use when I write it in my notes and on the solutions. And so this would be for, again, for the case where w is a function of x and y, and x and y are each functions of t. They have, oh, I'm fixing to sneeze. Don't sneeze. Okay, they have in your notes, excuse me. Okay, they have in your book, on page 715 is the first one, these, they call them branch diagrams. I don't really love the way this book does it. I learned it a different way in the old book, and I think it's much, much easier to follow. So I'm going to point them out in the book, but then in a minute when we get done, I'm going to show you how I do it. And I think the way I do it makes a lot more sense, surprise, surprise. But you can choose. You can do it either way. When I do my solutions, I'll do it the book's way and my way, and you can pick which way you like better. But this would be the book's way. I'm not really going to talk about it here because I'll explain it to you with my way, and then I think it's easier to explain with my way, and then you can go back and look at the book's way and see how this works. But anyway, that's a branch diagram is what your book calls it. The book that I learned it out of initially, or taught it out of initially, called it a tree diagram. So I may use the terms interchangeably. And again, you can use the book's way or my way. Okay, so they talk about it above example 1. You can go back and look at that later, this paragraph above example 1. They kind of talk about it if it's at a particular point that you're plugging in. Okay, so next case, this is Theorem 6 on page 716. This would be, now notice what's different. Now w is a function of x, y, and z. So w now has 3 pieces, but x, y, and z are all, they didn't write it, but they're all functions of t. So it would be like x equals x of t, y equals y of t, z equals z of t. So they're functions of just t. So when you take the derivative of the w, it's going to be partial derivatives because multiple variables. When you take the derivative of x, y, and z, it's going to be regular derivatives because they're a function of just t. So here's the formula. The dw dt, and so you have, and notice here, this is not really legal math, but it's a good way. I'm going to show you something. Don't actually do this, but it's a good way visually to make sure you set the formulas up right. So if you are on a test and you're trying to remember the formula and you're not sure you set it up right, here's kind of a way to double check yourself. Again, don't actually do this because it's not legal math, but just to show you. Notice on the left, let me get something to point with here. Notice on the left, it's w on top and t on the bottom. All right, and then look at each of these individual pieces. Again, not legal math, but if you imagine that you cancel out this curly dx and this straight dx, see how if you cancel them out, it's w on the top T on the bottom. Same thing here. If you canceled out the Y's, W, T, cancel out the Z's, W, T. So all of them are set up in such a way that if it were where you were able to cancel those, see how they would all just be the DW, DTs? So just a way to check and make sure that you set your formulas up correctly when you're doing these on your own. Okay, so here is their diagram. I'm going to show you mine in a minute. I'll get to those. They're all on one page. It'd just be easier to show it to you all together in a second. But they talk here, I want to show you this while we're here. At the bottom of page 716, they talk about a physical interpretation of this, kind of what's actually going on when you do these partial derivatives. And so there's two situations. There would be the situation that we were just talking about where x, y, and z are functions of just t. So a good way to think about that would be like something that changes with respect to temperature. And so the parameter t could represent temperature, or it could represent time. That probably makes more sense. But here they talk about temperature. And so as the time or the temperature changes, then these functions change. But it could be, and they talk about this at the bottom of page 716 on to the top of page 717, it could be that the functions, the x, y, and z, are functions of two variables, r and s. And so that could be, here's just one of many examples, but maybe you're looking at longitude and latitude. So maybe r is the longitude and s is the latitude. Don't remember that because it doesn't matter. But just as an example of why you would have functions of two variables, maybe you're looking at how something changes as it moves through longitudes and latitudes, and so it would be functions of two variables. And so in that case, if you have where the x is a function, so here we are up here, this is the top of page 717. If you have where the x is a function of two variables, the y is a function of two variables, and the z, if you have it, is a function of two variables, then notice when you plug everything in and you write the w, notice that it's now a function of two variables. And so before w, if you plugged everything in for x and y, or x and y and z, was a function of just t, but now it's a function of r and s. And so if it's a function of r and s, when you take the derivative of w, not only is it now going to be partial derivatives because it's a function of multiple things, but it's going to have two of them, one with respect to r and one with respect to s. So they have a picture and kind of an explanation here under the box, so you can look at the explanation later on your own. I highlighted it there so you could see where it was. And then they have some pictures. Again, I'm going to show you my pictures, which I think are better. I'm going to come back to this formula, the Theorem 7. The book does this a little bit out of order, I feel like. So I'm going to come back to the Theorem 7, and we're going to move instead to page 718 at the top, and we're going to look at this case first, just because this is a smaller case and that it's a function of two variables instead of three, so it makes sense to look at it before the other one. So top of page 718, here you have w is a function of x and y, x is a function of two variables, y is a function of two variables. So notice again, two answers, the partial of w with respect to r, the partial of w with respect to s, and then here's the formula. So you have w with respect to x, x with respect to r, derivative of w with respect to y, derivative of y with respect to r, and then same thing over here with the s's. So they have their picture here that you can look at. And now let's go back to Theorem 7. This is page 717. Notice Theorem 7, what's different is it's x, y, and z now. So x, y, and z, two variables for x, two variables for y, two variables for z. So again, two answers, and it's the same thing. It just has these extra pieces here for the z. So I'm going to show it to you now in my notes. And again, the notes are available on Angel. I kind of have it, I don't know if I can do this very well horizontally. Anyway, I have it here kind of all summarized together. I did it in the order of the book. So these two I feel like are kind of backwards, but whatever. So I would switch these two if it were me, but I did it in order of the book. So I have the four different types here, but really it's two main types. Theorem 5 and 6 are one type because they have, notice here, the functions are a single variable, just t's. Okay, so that's one type. And then Theorem 7 and the box with no name, they're the other type. Notice they are functions of two variables, r and s. Okay, so you don't want to have to really memorize the formulas because the letters change. And a lot of the problems, they use different letters. And sometimes they're using w, sometimes they use z, sometimes they're using r and s, sometimes they're using u and v. So they change the variables. And so don't try to memorize it. I'm going to show you a better way. And this is using what I call the tree diagrams, which is my version of what the book does with these little rhombus things. I don't know, diamonds, whatever shape they are. Okay, so here are the cases in the order I feel like they should be. So if you have w is x and y are t's, what you do is you start with the main one, the w. and then W has X's and Y's. So you branch off from W into X and Y. And then X is just T, so you go from X to T, and Y is just T, so you go from Y to T. And then as you go down each branch of this tree diagram, whatever's on top goes on top, and whatever's on bottom goes on bottom. So if you're going from W to X, it's dW dx. And then if you're going from X to T, it's dx dt. And the way you can tell whether to use a curly D or a straight D is look at how many variables there are. So in W, you see 2 variables, so you got to use curly Ds. But in X and Y, you only see 1 variable, so you use straight Ds. If it's 1 variable, straight Ds. 2 or more variables, curly Ds. That's how you can tell. All right, so same thing here. So you can see these branches, or the ends of these, they only end in T, so there's only going to be one answer. There's going to be the, I guess it would help if I wrote that. Let's write that on here. dW dt would be the answer, a single answer, and it's going to be dW dt. All right, next one. Only thing different now is you have X, Y, and Z. So from the W, branch off to X, and then to Y, and then to Z, and then each one of those just ends in a T. So again, here you're just going to end up with dW dt. And then again, whichever variable's on top goes on top, whichever variable's on the bottom goes on the bottom. So notice here W's on top and then the X, but now here X is on top and then the T. And so when you write these out, you're just, as you, I guess it would help if I wrote these out. Goodness gracious. Okay, if you go down a branch, then you're multiplying. So let me write this real quick. So, whoops, curly D, dx, and then I'm going down the branch, so I multiply, dx dt. And then when you switch over to another branch, now you add. So I have dw dy, straight D, dy dt. That's supposed to be a straight D. Okay, so see how if you're going down the branch, you multiply, and then when you jump a branch, you would add. So you try this one on your own. I'm going to write it. Can I fit it? I don't know if I can fit it. I'm going to try. All right, so again, down the branches multiply. So D, oh, I won't say it so you can write it on your own. I'll be quiet. You write it on your own. I'm not going to be able to fit it on one line. All right, so that's super messy. I hope you can read it. I don't know. So it should be curly dw, curly dx, straight dx, straight dt, plus curly dw, curly dy, straight dy, straight dt, plus, this is down here, curly dw, curly dz, straight dz, straight dt. All right, so that's the way the branch diagrams work for those. Now let's look at the next case. These would be the 2 cases where your x and y and z, if you have it, are functions of 2 variables. So first case, w is a function of x and y. So you start from w, branch off to x and y. And then x is r and s. So x branches off to r, x branches off to s, and same thing with y. So notice here, if you look at the bottom, see these at the bottom, all you saw were t's. 1 variable at the bottom, 1 answer. But here, 2 variables at the bottom, 2 answers. There's no way I'm going to be able to fit it here, so I'm just going to write what you're finding, and then I'll flip back to the page with the formulas. But these would be your 2 answers. Notice they start at W. Whoops, wrong one. Here we go. Start at W, and they end in either R or S. So it starts at W, and it ends in either R or S. So 2 separate answers. And so, again, as you go down the branches, multiply. And then, so here, the first one, you're going to go down any branch that ends in an R. dw dx times dx dr. And then over here, dw dy, dy dr. So only the branches that end in R. And then for the next one, only the branches that end in S. So dw dx, dx ds, dw dy, dy ds. And so the formulas would look like these. Okay, these are on page 718 if you'd rather just look at them in your book. So this would be for when you have x and y. Okay, now lastly, x, y, and z. So w branches off to x, y, and z. Each of x, y, and z branch off to r and s. So you have 2 different letters at the bottom, so 2 different answers. So again, dw dr, dw ds. So again, for the formulas, for the first one, follow all the branches that end in an r. So you would go this way, you would go this way, you would go this way, following the branches that end in an r. And then for the next one, following the branches that end in an s. So this way, and this way. So two different answers. So this is what in my solutions, I call this my way because it's the way I do it. And then the book, they have these like this. I don't like these quite as much because they all have the same shape. But then if you are going to have a function of two variables, hold on, let me find one. See, then they have to make two of them. So see how for dWdr they make one and dWds they make the other. So you have to have two separate pictures. I like mine because it's all one picture. So it just makes more sense to me. Whichever one makes more sense to you, do it that way. It's totally up to you. It's all about how you learn better. So whichever one you like better. Okay, next, you're going to love this. Prepare to be amazed. If you remember from 3.6 maybe? Don't know. Who knows? Somewhere in Calais. If you remember from somewhere in Calais. No, I don't think that was 3.6. Who cares? It was the end of chapter 3 somewhere. Implicit differentiation. I think 3.6 was chain rule, so it would have been sometime after that. But implicit differentiation in Calais. Do you remember how, I don't know if you remember this, but you had to go take the derivative of everything, stick a dy dx on the end of any time you took a derivative of a y, sort them out, move the pieces with the dy dx to one side, the pieces without the dy dx to the other side, factor out the dy dx and divide. That's a big pain. This is the bottom of page 718. This is implicit differentiation revisited. And so it's showing you how, I think this is funny, it takes some of the algebra out. So it's pretty much all calculus and no algebra, which who doesn't love calculus? So first, the important thing is that you rearrange it, whatever it is that you're trying to integrate, you have to rearrange it. You got to get it equal to 0. So you got to get it equal to 0. That's very important. And then when you get it equal to 0, so moving back up here to page 718, and they show you why. I'm not going to go through the why because it's pretty easy to follow and let you look at it on your own. But the bottom of page 718, they start talking about it, and the top of page 719. So I think sometimes if you look at where a formula comes from, it makes it easier for you to remember it. So if you want to take some time and look at that, this video is already going to be ridiculously long, so I don't want to take some time to look at it right now. But if you look at it, it will explain why it works this way. But it turns out that the dy dx, that's what you were trying to find in implicit differentiation from Calais, is just, and notice this capital F, that's this f of xy that's equal to 0. Okay, so we'll look at an example in a minute. But anyway, if that capital F is equal to 0, then this would be the partial derivative with respect to x. This would be the partial derivative with respect to y. And you just stack them on top of each other like this and put a negative out front. That's it. Super easy. So they have example 5 here you can look at, see very little work. It's much easier than doing it the Calais way. And then here they talk about how you can do it for x, y's, and z's as well. But if you do it with x, y's, and z's, now there's going to be 2 answers because you've got, here this makes more sense. If you look at it, x is a variable, y is a variable, z is a function. Z is a function of x and y. So you've got the derivative of this function with respect to x and the derivative of this function with respect to y. So there's 2 answers now. So again, they explain it here. I'm not going to take the time to do it because this is pretty easy to follow. But at the bottom of the page, the partial of z with respect to x, again, you're just stacking partial derivatives, sticking a negative in front, and the partial of z with respect to y. So a much, much easier way to do implicit differentiation. Okay, and if you're interested, on page 720, they have functions of many variables. This would be what if it has more than 3 variables, because 3 variables is the biggest case we looked at. So you can look at that on your own. We're going to pretty much stick to 3 variables, so this would just be 4 if you needed it for something else. Okay, finally, problem 721, page 721. This one, let me just go ahead and warn you, the first few problems, 1 through 12, they're extremely long because they're having you do it 2 different ways. I think it's really important that you do it both ways because it helps you to conceptually understand what it is that's going on. So you're doing it using chain rule, which is something that may or may not make sense to you because it's new, but then you're doing it a different way and you can see in doing it both ways how it's connected and how it makes sense and what's really going on. So please, please do it both ways, like the directions say. It's very important, again, for a conceptual understanding of what it is that's happening. So you can see what I'm talking about. If you look at 1 through 6, you're expressing dw dt as a function of t, and here's the 2 ways, both by using chain rule and by expressing w in terms of t and then differentiating with respect to t. So, and then in part b, you're plugging in the number. So again, please do it both ways. I think it will really help you to understand. It's only 1 through 12 that you have to do that on, and then when you get past that, you can just do it just chain rule, but it'll really help you to understand chain rule better if you do that. So we are going to look at number 1. So here's, why did I do number 1? I usually do even ones. Who knows? I don't know why I did number 1 instead of an even one, whatever. Okay, I should give you an even one for homework then, just to make it fair. Just kidding. I'm not going to do that. Okay, number 1. Here's the problem. Notice x is a function of just t, and y is a function of just t, so single answer here. Okay, so using chain rule, I wrote the formula. I would highly recommend every time writing the formula for 2 reasons. 1, it'll help you, get used to these formulas, and 2, then when notice there's 4 pieces, this piece, this piece, this piece, and this piece. You can make sure you get the right pieces and put them where they go. It's just kind of a template to follow, I guess. Okay, so the derivative of w with respect to x, x is a variable, y is a constant, so 2x plus 0. Derivative of x with respect to t, negative sine t. Derivative of w with respect to y, x is a constant, y is a variable. Did I say that right for the dw dx? I don't know. I don't know if I said that right. Now that I think about it, I wonder if I said that wrong. But I'm not going to rewind to figure it out. So dw dx is x is a variable, y is a constant. dw dy, x is a constant, y is a variable. So 0 plus 2y. And then dy dt is cosine. So again, here you're multiplying and then adding and multiplying. So you get this. So negative 2x sine t plus 2y cosine t. Okay, now doing it the other way. So I should get the same answer. I'm just doing it a different way. So what you're going to do is... Oh, sorry, no, I'm not finished. Just kidding. So they have you do this extra stuff here so that you can compare answers. So I'm sorry, I'm not quite done with this piece yet. But now, so that I'm going to be able to compare answers, I don't want to have x's and y's mixed with t's. So I want to be just t's. And so to be just t's, I need to get rid of the x's and y's. So to get rid of the x's and y's, I'm going to plug in for x and y. So I'm going to plug cosine t everywhere I have an x, sine t everywhere I have a y, into this answer here. So in place of this x, plug a cosine. In place of this y, plug a sine. And then notice those are the same thing, but one's positive and one's negative, so that's just 0. Okay, now I'm finally done with that part. Now I'm going to do it another way, and again, now I should get the same answer. I wouldn't have gotten the same answer if I hadn't have done this, because my other answer is only going to have t's in it. So if I hadn't have done this, they wouldn't be the same answers. Okay, now, other way. Express w as a function of t. So now at the very beginning, plug in for x and y. So back up here at the very beginning, plug in for x and y. So I have this, which is just 1. Now take the derivative of that, 0, same thing. Okay, so that's just, again, 2 different ways to do the same thing. Part B is plugging in this value for t, but there's nowhere to plug in this value for t, so it's just 0. So I'm done. Okay, that's number 1. My headphones are falling off. Hold on. I don't really need headphones, but I need the microphone so you can hear me better. Okay, much better. Number 6. Same thing, but now I have x, y, and z. And so again, notice that they are all functions of just t. So I'm going to have one answer. But again, I'm doing it 2 ways. Okay, using chain rule. Again, write the formula first step every time so you make sure you get all the pieces where they go. So dw dx, x is a variable, x and y are constants. dw dy, y is a variable, x and y are constants. dw dz, z is a variable, x and y are constants. Okay, so for the first one, it'll be 0 minus, and then by normal chain rule, Cal-A chain rule, derivative of sine is cosine, don't mess with this, and then derivative of this, and then dx dt is just 1. Then for dw dy, 0, again, normal Cal-A chain rule, derivative of sine is cosine, the minus was already there. Don't mess with this, and then the derivative of that, and then the derivative of y is 1 over t, and then it wouldn't all fit on one line, so continuing on. The derivative of z with respect to z is 1. This is just 0. And then derivative of z is e to the t minus 1. And the derivative of t minus 1 is just 1. That's again by regular chain rule. Okay, so cleaning it up a little bit, I get this. But again, that's not going to match my answer doing it the other way if I still have x, y's, and z's mixed with t's. So I need to get it to be all t's. Just again to compare answers, not in general necessary. I just realized I forgot to check my answers. I usually check my answers in the solutions manual just on the off chance, well, not off chance, just on the chance that I did something stupid and I forgot. So hopefully none of these are wrong. I'll check it later because I can't pause this video because I'm not using that app. And if any of them are wrong, I'll let you know on the video sheet. But hopefully they're all right and hopefully I didn't do anything stupid. We'll see. Okay, anyway, plug in for x, y, and z into this answer. So get rid of the x, y's, and z's and get it all in terms of t. So plug in for the x and y and z these equations up here. plugging all that in simplifies down to this. It's kind of messy because I didn't put these brackets around it the first time, and so I didn't realize that ln of t was part of the cosine. So be careful there. It's the cosine of t times ln of t. All of that's part of the cosine, so you can't switch it around. All right, now the other way. So expressing w as a function of t, plug in x, y, and z into your w. So that's back up here. So plug in x, y, and z here and get a new function. So plugging that in, it simplifies down to this. And then taking the derivative, notice this answer and this answer don't look the same initially, but if you took these two pieces and you factored out the negative and the cosine, then it would be this. Okay, so they're equivalent, they just don't look exactly the same because this one is not factored. Or here you could distribute, and if you distributed, then they look the same. All right, now you're going to plug in, they told you up here t was 1. You can plug the t equals 1 into either equation. I happen to use the second one here just because it was closer, but you can plug it in here too, you get the same answer. Okay, so plug in t equals 1, and notice that ends up just being, coincidentally, 0 again. They're not all 0. Okay, so that's the first group of problems. That would be for where you have just t's. Now let's look at the next group of problems. This is 7 and 8. Now you have, notice instead of R and S, like the book's formula, you have U's and V's. So again, that's why I was telling you don't memorize it in terms of the letters, just memorize how to come up with the formulas because the letters change. All right, so again, you're doing it both ways. Using chain rule and then changing it up and then differentiating. Not changing it up, plugging it in, whatever. Number 8. Okay, jeez, my paper. Okay, so here, again, notice U and V, U and V. So there's going to be two answers, the answer with respect to U and the answer with respect to V. All right, using chain rule. Here's the formula with respect to U. I'll do the V1 in a minute, but here's with respect to U. So for tangent inverse would be 1 over 1 plus x squared normally. But here it's 1 over 1 plus this squared. But then by normal Cayley chain rule, then you have to take the derivative of this. And so that's this piece. So it's the derivative of whatever was here. That's there. And then times the derivative of x with respect to u. And then now take the derivative with respect to y. And then the derivative of y. And then cleaning it up a little bit gets me to here. Distributing the y and the y squared gets me to here. But notice this one is still a complex fraction. Complex fractions are not okay. You do not want complex fractions. So to fix this, so this is not a complex fraction anymore, you want to multiply this piece by y over y. So if you multiply by y over y, it becomes y cosine b and then y squared plus x squared. Then it's not a complex fraction anymore. Okay, now again, this has u's and v's and x's and y's. You want to get it down to just u's and v's. So you're going to plug in for x and y. And then notice, I didn't show a whole lot of work here because this was a big mess, but notice this is u sine v cosine v minus u cosine v sine v, and they have the same denominators. So since they have the same denominators, you can put the numerators together. The numerators are the same thing. One's positive, one's negative, such as 0. Again, they're not all 0. Just happens to be, for whatever reason, the ones I chose ended up being 0. Who knows? Okay, next one. dz dv. Everything's with respect to v. And notice a little time saver. Look here. See dz dx, dz dy. Notice here, dz dx, dz dy. Those pieces don't change, so you can reuse them. They're the same. The only thing that's changing is here it was here it was u's, and now it's v's. But the first two terms of each, the first two pieces of each term don't change. So you can just copy them from above. So this is the same as from above. This is the same as from above, and then this piece and this piece are new. So these are the new pieces. Again, cleaning it up. And here I didn't show the step because it was the same issue, still a complex fraction. And so I just multiplied by y over y. So going from this step to this step, I just multiplied by y over y to fix the complex fraction. And then notice again, same denominators. So you can put them, oh, just kidding. I didn't put them together yet. You could put them together and then plug in for x and y. I plugged in for x and y and then put them together. The order is not important. It's the same. Okay, plugging in for x and y. This one, they're not the same, so it doesn't cancel out to be 0, but they do have the same denominators. So since they have the same denominators, you can put the numerators together. And then when you put the numerators together, you can factor out a negative u squared from the top. You can also factor out a u squared from the bottom. And so sine squared plus cosine squared is 1. So this just ends up being negative u squared over u squared, which is just negative 1. And then next in part B, I would have had to plug in that point. But notice these are just constants, so there's nothing to plug into. So that makes that easy. Okay, now express z as a function of u and v. So plug in for x and y first. Plugging in for x and y first gives me this. Now take the derivative. Notice in this, there are no u's. If there are no u's, then when you take the derivative with respect to u, that's just a constant. It doesn't look like a constant, but it is. And so the derivative is just 0. So that's super easy. Way easier than the other way in this case. Okay, but now for the derivative with respect to v, it's tangent inverse. So it would be 1 over 1 plus whatever you're taking the inverse of squared. But then the derivative of that, so when you take the derivative of that, I did chain rule. I mean, not chain rule. We're doing chain rule. But I did quotient rule. In hindsight, it probably would have been easier to just write that as cotangent. But whatever, too late now. So I did it with quotient rule. Okay, so this is my simplification. And notice here, this is in the bottom. So I put that in the bottom, and then I can distribute it. And then in the top, I factor out -1. And sine squared plus cosine squared is 1. And then in the bottom, when I distribute it, I have sine squared plus cosine squared, which is also 1, so just -1. So again, because they're constants, there's no numbers. There's no need to plug in the point because they're already just numbers. Okay, I'm tired. All right, so that's all of those. There's more. If you really like those and are enjoying doing them, there's more in 11 and 12 and 9 and 10. The concepts are the same, just more variables. But now let's look at some of this next group, 13 to 24. 13 and 24, draw a branch diagram and write the formula for each. So 2 things here. I'm looking for the branch diagram, either my way or the book's way, and the formula. So don't forget to do the formula. All right, I'm going to do 14. I've got it both ways here. So 14, z branches off to u, v, and w. So z, u, v, w. And then each of those are just t's. So they end in t's. So because that's all t's, it's just one answer. So again, you're following the branches. Whatever's on top goes on top. Whatever's on bottom goes on bottom. So dz, du, du, dt. dz, dv, dv, dt, and so on. But notice z, because it has multiple variables, curly d's. Okay, but u, v, and w, single variables, so straight d's. So very important, curly d's and straight d's are not the same thing. So make sure you use the appropriate one. So single variable, straight d, 2 or more variables, curly d. And then here's the book's way. Z branches off to u, v, and w. Each of those branch off to t's. So it's the diamond or whatever shape that is. Okay, let's do a couple more. If my paper would be still, that would be great. Okay, this is 16. Here, notice you have RS and T for your W, and then each of the RS and T's are 2 variables. So it's like they swapped them here. Usually it's the X and Y and Z here, and the R and S here. They swapped them to make sure you can understand this conceptually instead of just memorizing the letters, because if you memorize the letters, they're going to be backwards here. Okay, so 2 variables over here, so 2 answers over here. So with mine, you can do it in a single diagram. With the books, you're going to need 2. With the books, you're going to need one that ends in X and one that ends in Y. With mine, you can see I have X and Y's at the bottom. So W branches off to RS and T. RS and T each branch off to X and Y. So first you do X's. Well, it doesn't matter what you do first, but first I did X's because it comes alphabetically. So you're following the branches that end in X. So just follow the branches that end in X. For this first one, all of these are curly D's. And then for the Y, you're following the branches that end in Y. And again, all curly D's. So two separate answers here because you have with respect to X and with respect to Y. All right, last one of these, and then there's another problem, so don't get excited. We're not done yet, but this one's almost so easy that it's hard. This one, there would have been 2 answers when you're taking the derivative of y. See, that's why it's a curly D. There would have been 2 answers because y is a function of u, but u is a function of r and s. So there could have been dy dr, or there could have been dy ds. They didn't ask you for dy ds, so you don't have to do it, but just be aware there's 2 answers here. Okay, so y, looks kind of weird. Y goes just to u, so y just to u. But then u goes to r and s, so r and s. So this is my way. You can see there's 2 different variables at the bottom, so there would be 2 answers, but again, they only asked for 1. This is the book's way, and you would have needed a separate one for the s. So if they had asked for dy ds, then you would need y u s. They didn't ask for that though. So this one is just got a couple, one single term that's the product of two separate pieces. Sorry, my nose is running. Oh, okay. Having issues today. All right, anyway. Where are we? Okay, next. Oh, and plus the differentiation. You're going to love this. It's so much better this way. Page 720. Well, you can't see that, but 721 still where I'm at. 25 to 28, it's dy dx. Because notice here in all four of these, it's just x's and y's. So if it's just x's and y's, you're finding dy dx. Okay, so make sure it's equal to 0. All of the ones in the book are equal to 0, but just be aware that that is a requirement, so you should always check it. Must be equal to 0, check. All right, so the capital F is this thing that's equal to 0. So the capital F is all of this. Now I need the partial with respect to x and the partial with respect to y. So partial with respect to x, you're just going up here and taking the derivative with respect to x. Partial with respect to y, same thing, but with respect to y. So I get, after I simplify, these two partial derivatives. Then all I have to do is stack them. So x goes on top, y goes on bottom, put a negative in front. So here, the negative needs to either stay in front with parentheses or be distributed. If you put it in front without parentheses, then it'd be wrong because it gets distributed, so it needs parentheses. Okay, and then they want you to plug in this point. So you're plugging in this point for x and y. Oh, apparently it's on the next page. Okay, so plugging in this point for x and y, I get 2. So because this is at a point, your final answer should be a number. Okay, so this answer is 2. All right, let's try one in the next group. Find the values of dz dx and dz dy at these points. So notice in these problems, x, y's, and z's. If they're x, y's, and z's, remember x is a variable, y is a variable, z is a function of x and y. So you've got two answers, z with respect to x and z with respect to y. All right, so again, must be equal to 0. Again, it is, so check. Capital F is the thing that equals 0. So it's all of this. And then now you need 3 partial derivatives. So you need the partial with respect to x, the partial with respect to y, and the partial with respect to z. So you just go through and find those. These are pretty basic. Notice that this is constant, a constant always, and this is a constant always. So always those two pieces are going to be 0. All right, and then for dz dx, x goes on top, z goes on bottom, stick a negative out front, so it would just be this. And then I went ahead and plugged in the point before I found the next one. So plugging in the point, when there's direct contact between the e and the ln, they cancel. And so those two cancel, and it just leaves me with negative 4 over 3 ln of 2. Then I would do the same thing, dz dy, y goes on top, z goes on bottom, stick a negative out front, plug in the point and simplify, and it's negative 5 over 3 ln of 2. Okay, so that would be for x, y's, and z's. 2 answers on those. All right, finally, I know this video is long, sorry. Finally, at the bottom of page 721, 33 to 38, they're having you find partial derivatives at specified points. So same thing, basically, that you've been doing on why they separate this out. But anyway, whatever. Here, you're trying to... Notice here they're just asking you for one piece. This would have 2 different answers. It'd have dwdv and dwdu, because see how here you have u's and v's? Well, in here you just have u, but anyway, u's and v's. And so there would be 2 answers. They're only asking you to find one. Only find what they're asking you for. Don't do extra. Well, I mean, unless you just want to for extra practice, but you don't have to. Okay, just find what they're asking you for. So, start with the formula. Always start with the formula. Put the pieces where they go. So, ignore this up here. That's for the point that you're going to plug in later. So ignore those numbers. And so you're looking, here's the w, and here's the x, y, and z. Okay, so hopefully you feel comfortable enough with derivatives now that you can do these on your own. And so I end up with this. All right, so now, oh, I see, this is different. That's why they separated it out. Now this you have to plug into, but notice they only gave you u and v. They told you what u and v are, but you don't know what x and y are. So what you can do, 2 choices. This first way is not the way I'm going to do it, but this is a possibility. You could do like we were doing before. Take this function for x, plug it in, take the function for y, plug it in. You can do that. Or you could just figure out what x and y are. So come over here, figure out what x and y are in terms of numbers. They told you what u and v were. You know the functions for, oh, I didn't write the function for y. Y was u plus v. Okay, y is u plus v. X is v squared over u. So anyway, you just plug in for u and v, and that gives you x and y. So x is -4, y is 1. Now you can come back over here and plug in for u and v and x and y, and it simplifies down to -8. All right, so that's all from this section. This section and the previous section, 13.3 and 13.4, extremely, extremely important because just like in Cal A, when you learn derivatives first and then you learn integrals next, that's where we're going in Cal C. So if you can't do derivatives, you can't do integrals. So it's really important that you understand this. So practice, practice, practice. Do as many problems as you can until you get the hang of it and you feel comfortable doing this. So that is all from this video. Again, if you have any questions, just send me an email.